Yeah. Yeah, so there will be a group going to the Banksy exposition tonight, so if you want to join. Yeah, so let me a little bit summarize what we've done last time. We defined Hurwitz numbers. And then we said, OK, they are connected and disconnected. These ones, you have many partitions. And they are this 1 over the degree factorial. What's the degree? It's just the size of any of these partitions, eta i's. And then you want to count how many times you get the identity out of the product of the C eta i's. What are the C eta i's? They're just the sum, the formal sum of all the permutations that have a cycle type eta I. What's a cycle type? Is the underlying partition. So you just count the length of the cycles. OK, and then there was a similar statement here. This one is simpler, I would say. Why is that? Because here you don't need to worry. Which means that you actually expand each of these CIs. It becomes very big. Then you take the product. It becomes huge. And then you select how many times you get identity. Just count them one by one, no problem. You divide by d factorial. You're done. Here it's a little bit trickier. When you take these products, you need to be careful and only take the 2+ of those elements that span the transitive subgroups of SD. So you have to check product by product that what you're doing is OK. Cool. And so let me now show you a little trick from representation theory. So many of you will know this, but still, it's very useful here. If you take the group algebra of the symmetric group, you have 2 different bases. You want to define these elements F delta. You want to define them as, why do you write delta? No, rho. So rho is a partition. Rho is a partition. And also lambda. And let's recall that like an irreducible representation of the symmetric group in bijection with the conjugacy classes and there's also same thing with Young tableau. So you have this sort of, I mean, you all know this, but just to recall, if you take the partition 5, 3, 1, 1, then you can associate this kind of object. 5, 3, 1, 1, right? Good. And so now what you want to do is the following. You take F rho, that is defined as the dimension of rho, as irreducible representation. And now you divide by your d factorial. D is always the size of the partitions. And here now you sum over lambdas, such that their size is d. And here you want just to put the character of the irreducible representation rho, evaluated at lambda, and then you take C lambda. And C lambda, you can invert this, and now C lambda turns out to be the cardinality of C lambda times the sum over rho, again, partitions of D, character rho lambda, F rho, dimension of rho. So I'm just doing a change of basis. Just doing a change of basis. But now there is a little magic. Now there is a little magic, and this magic is that the orthogonality of characters it implies, and it is basically equivalent to, the fact that the F are idempotents. I mean, just try, right? F is defined like that, and then the C's are defined like the F, and now you take this guy and you substitute it back in here, and you have an expression of F in terms of F. If you take the product of two F's over here, you will have a quadratic expression in the characters. If you exchange the sum and use orthogonality of a character, they contract, and then what you get is that F rho times F lambda is equal to F lambda. So F is very nice basis. That's the point. F is a very nice basis. It's basically like we knew orthogonality of characters, and then this change of basis is done on purpose. It's just done on purpose to get something nice. Okay, so how to use this? How to use this relation? F rho, F lambda is equal to delta. So this is the Kronecker delta. This is equal to 1 if rho is equal to lambda. And otherwise it's 0. Okay, how to use this? So if you take your Hurwitz number, G, and then this depends on several partitions. Eta 1, eta m. Now this, I'm taking the disconnected ones because it's easier. 1 over d factorial, and then you count how many identities you have in the product of the C eta i's. Now you can imagine what we're doing. We're just taking every C and we're setting F in it. We're plugging F inside. So it's 1 over d factorial, identity, and here you have products of, every time you see an F, you have to write this. So it's becoming like C eta I times sum over rho I, and here you have to put a lot of stuff, the characters of rho I, evaluated in lambda I, and then F rho I, and then this dimension of rho I, blah, blah, blah. But now you can finally use your nice idempotency, because you have the product of many F. And so whenever you have a product of many F, the index should just be the same. Right? I have product here from 1 to m, and here I have a lot of F. I have F rho I, F rho 1, F rho 2, F rho m. But now these guys are idempotent, so this should be equal to just F rho 1. And here you have the Kronecker delta such that they are all equal. Right? So what you get is 1 over d factorial. And here you're counting the identities inside the sum over lambda, d. And here you have product I from 1 to m. And then you have your C mu, C eta I, chi lambda eta I, F lambda, dimension of lambda. So lambda is the new partition that I set everything equal to. Sorry, this was eta I. Okay, and so eventually, if you finish this computation, what you get is now you're stuck with one f. Now you still have one f. Before you had a lot of them. Out of many of them, you just got one because of idempotency. But now you still have one. So what you do is you substitute back f equal to something in the C's. And so it's 1 over d factorial, and then it's the same thing. And now you express the f in terms of the C again. And now you look for the identity in here, and then it's easy, right? Because when you expand C in the F, and you want to take, sorry, F in the C, and you want to take the identity out of that, you have to here select lambda equal to 1, 1, 1, 1, 1, right? I want to look for the identity inside this expression, and the identity is 1, 2, 3, 4, D. That's the identity. So which means this is my lambda, and so lambda should be 1, 1, 1, 1, 1. This is the partition that is underlying the permutation. So out of here, you will get actually the character evaluated in the identity. But we know what that is. That is just the dimension of the representation. So this is just a dimension. I'm doing the computation a little bit fast, but it's fairly clear what is going on. You take each of the C and you substitute the F. It's just a change of basis. Then you use that the F idempotent. So instead of having many of them, you just have one. Now you still have one, and that's annoying. So you substitute back F in terms of the C, and now you say, aha, it's very easy to select what the identity is. The identity is just this permutation over here, which corresponds to this partition. So I know what to take. I have to take the character evaluated in the identity. That's just the dimension. And so at the end of the day, you get that this is equal to the sum of all the lambdas of size d. And here you have dimension of lambda divided by d factorial squared. Here you have the product I from 1 to m, c, eta I, chi lambda of eta I. And here you can divide by the dimension of lambda to the power m, if you take it outside of the product. So that's what people call Frobenius formula.
Question? Question, is there any relation of this Frobenius formula with the data of Frobenius manifold?
With
the data coming from the Frobenius manifolds?
I wouldn't say this direction is direct. Okay. No, Frobenius manifold is like huge world on the side, and this is just some combinatorial thing about like representations of the symmetric group. So
Okay.
Frobenius did a lot. So my point is that we started with this definition. Hurwitz numbers are honest count of covers. And then we said, this is hard to use. Let's go with something easier. And then we had this, this other statement. It's enough to use the group algebra. And then we just how many times we get the identity out of this product. But then if you perform this change of basis with the F, which are idempotent, then all of a sudden you're summing over irreducible representation of SD. So you have a new expression. And then you can compute the characters and so on. It's another way of computing. And for me, this is really like from here to here, it's a continuous refinement. In the sense that it's more and more sophisticated, the tools that you're using. And actually there is a 4, which is very nice. And it's the Hurwitz numbers as a vacuum expectation of operators. And that's what Okunkov did in 2000. And this implies KP integrability. Of Hurwitz numbers. And it really comes from here. It's really the last step of this sequence. I will write down I cannot define all the operators that you need to prove this from here to here, because there will be a lot of notation. It's not hard, but it's just long. I will just write the final result, because it's something that you can use straight away. Like if you don't know what these operators are and how they act on this space, it doesn't matter. There's just an algorithmic recipe. You just take this recipe, you put it in a computer, you compute by hand even, and you can just straight away use it to compute Hurwitz numbers. Sorry?
I think the Okunkov formula and the simplification by Dubrovin, Yang, and Zagi is just for unramified. Just like you don't have any lambda or whatever.
No, they
formula.
do. Definitely, yes.
Yeah.
Sorry, it's definitely ramified. Actually, there are two. If you remember, there is this 2. This 2. So at the end, you have dimension to the power 2 minus m. And sort of, there are 2 partitions. OK, I'm writing something intuitive. If you stare at this formula, you see that there are sort of 2 partitions that play a special role. And in fact, this integrability here is of type 2D Toda, which means simply that you have 2 sets of independent times. One is a ramification over 0, let's say, and the other one is a ramification over infinity. If you specialize one of the 2 to unramified, then you get KP. If you specialize also the other one to unramified, then you get the Hurwitz numbers that were, for example, computed a lot by Zagier and Dubrovin and Yang, in the paper that probably you're citing. But in principle, you have 2 sets of times, and that's what the first paper was about. So let me write here. What I mean is that I don't only care about the fact that this expression proves integrability, in the sense that the partition function is a tau function of some hierarchy, but it has been used many times, this level here, the level 4, to prove that some Hurwitz problem satisfies topological recursion. what people were doing a few years ago was, but even now, is to take this formalism over here. You have some Hurwitz problem. You look for the right operators that you have to put in here according to the ramification. But there are also other types of Hurwitz numbers that I'm not talking about now. And they have a different types of operators. But the structure is always the same. And now there is this algorithm to compute vacuum expectations. And by using this algorithm, you can prove properties that you need for the spectral curve. So what my claim is that you don't only compute Hurwitz numbers. You use this to do topological recursion. And the formula is the following. You take G. Let me put mu, nu, and then 2, 1, 1, 1, 1, 1 to some power b. Okay, so you have one partition over 0, let's say, over 0. And this one is over infinity. So you have something like that. This is P1. This is a map D to 1. This is infinity. This is 0. Here you have some genus. Here you have mu1, mu2, mu_n as ramification. And here you have mu1, mu2, mu_m. And here you have some fixed points. And above each of them, you just have a simple ramification. Just two sheets that come together above each of those. So these are the two sets of times of 2D Toda. And this is equal to 1 over the product of the mu i's times product of the nu j's. And then you take this vacuum expectation, and then I will write some symbols, then I will explain how they behave. You take this curly E of mu1 in 0, curly E of mu2 in 0, curly E of mu_n, 0. Then you take times, or maybe composition, but it doesn't matter. 0 zeta 1, 0 zeta b, minus nu1, minus nu_m. And then here you want to collect z1 to the power 2, z2 to the power 2, zb to the power 2. And then I have to write how these guys behave. The rule is that En of Z, Em of W goes like the hyperbolic sign of NW minus MZ divided by 2, and then you have a 2 here, and then you have E of N plus M Z plus W. And also, every time that you have E of something positive, this is 0. And every time you have E something negative, this is 0. And every time you have E 0, that's equal to 1 over 2 hyperbolic sine of Z. And the same is true the other direction.
2 questions.
Yeah,
please.
just 1 second. I'll finish this and coming. This way. Okay.
So, first question is about, you said about topological recursion in the case of Hurwitz numbers, and at a certain point I would really like to see what is the spectral curve in that case. And the second question is about this E, are they a representation of Virasoro algebra, I imagine?
Okay, so for the spectral curve topological recursion, that's the next part that is coming. And for, yes, there is, well, there is definitely a Virasoro algebra for Hurwitz numbers. These particular elements are elements from GL infinity hat, which means that you have infinite matrices in both directions, such that elements are 0 when they're far enough from the diagonal. So you have non-zero stuff here. Yeah. I know I shouldn't write on this spot. Yeah, thanks. 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 Sorry that we're using all your pens.
Then if you can write the indices a bit bigger.
The index is a bit bigger. Okay. So what I want to convince you of this expression is the following. So I just wrote some big expression that doesn't make any sense. And I didn't explain any of these objects. However, my claim is that these properties here are enough for you to compute straight away.
On the left, it's shown positive, it's 3 points, or it's the left over.
Sorry? This one.
The first line on the left of E positive, just below. Is there a left angle or it's 3 points?
No, every time this operator with some positive index hits the vacuum, then everything vanishes.
It's Fourier components of vector fields, I think, on the symplectic vector fields on torus.
You're too advanced. I don't know.
Yeah, it's a Fourier
Okay, I believe you. But I'm saying something way simpler than that. I'm saying that there is an expression, and Okunkov computed it. And this expression is interesting because it implies integrability, and moreover, it's useful for topological recursion, and you can use it straight away to compute Hurwitz numbers. How does it work? Hurwitz numbers are equal to, okay, you have to divide by the nu I and by the nu j's, so that's very easy, right? And then here you have some weird angles and some stuff inside. But then there are these variables z. And how many do you have? You have b of them, the number of simple ramifications. So how many they are? B is just 2g minus 2 plus the length of mu plus the length of nu. This is exactly a Riemann-Hurwitz equation that we've done yesterday. Okay, so you have all these variables, whatever. They are inside. I can tell you that these are just analytic functions, except they can have a simple pole. So at most they have a simple pole in the zi's, but at the end of the day, you have nothing actually. Even if this guy starts with 1 over z, then at the end of the day you have nothing. And then you just select the coefficient of z1 to the power 2, z2 to the power 2, up to zb to the power 2. So that's very easy.
It's the same thing again. Now B is not. So why 2g minus 2?
No, it's really 2g minus 2 plus length of mu plus length of mu. For connected ones, you will have to. Yeah, okay, sorry. Because I didn't want to make this statement for the connected ones. There is one subtlety. It can happen that if you take, say, curly E of 5 of Z, and now you commute it. So let me first state how this computation would work, and then we come to your question. So now you have all these symbols, and you want to get a number out of this expression. How do you do this? Okay, so you just use this commutation relation, because you know that many things will vanish. Many things will vanish. So every time you manage to carry one E with positive index at the end, all the way to the right, then you won, because that thing is 0, so you don't have to worry about it, you discard it. And vice versa, every time you manage to carry something negative to the left, also you don't have to worry about it, that's 0. And every time you manage to carry some 0 over here, you just also get rid of this and then get a hyperbolic sign. Now you expand hyperbolic sign, and you select z to the power 2, you're done. So that's all steps that we know very well, right? So we basically, at the end of the day, we just want to commute operators to bring the bad guys on the right and the good guys on the left. So how is the commutation working? If you take two guys with arbitrary index and arbitrary variables, the answer is just that you need to sum their indices, their energy, and sum their variables. That's it. But what you created is some hyperbolic function of a combination of the two. So every time you commute, you create some hyperbolic function. So you would expect that at the end of the day, at the end of this big process, you have a vacuum expectation of E0 of Z. This is and here you have product of many hyperbolic sign with many stuff in it. This is going to be a big mess. But at the end of the day, you just have vacuum expectation of 1 E0. And what do? You just get rid of this and you create another hyperbolic sign downstairs because of this property. So at the end, you just have ratios of hyperbolic sign. Then you expand in power series. Then you select Zi to the power 2. And then you get a number. This is how it works. And then to answer your question, actually, you have both statements, connected and disconnected. How do you detect which ones are connected ones? Well, you just, every time that you have an E0 that splits your computation in two guys, like that, you have many E's on the right, many E's on the left. Every time you have something like that, then you discard it. Because this guy corresponds to, you have some genus here, you have some genus here, and you're covering D21, the sphere. Every time you have products of vacuum expectations, that's going to be disconnected. You just want to select the only one that stays connected all the time. So now I want to talk about the export log principle. Which, of course, many of you know. And there were already questions about it. But it's still something very useful in enumerative geometry. Like, if you are working with your favorite problem, and it's not Hurwitz theory, you usually, when you're counting geometric stuff, you often have this connected objects and these possibly disconnected objects, and this principle keeps holding even beyond this topic. So I think it can be quite useful. But let me just state it for this particular problem. So you want age that is a power series in U, and then in Q, and then you have this Pij's. And you want to define this as big sum of G. Then you have M, then you have D, and then you have your etas. And here you have your Hurwitz numbers, A to G. You have all the eta. Then you have 2, 1, 1, 1, 1, 1 to the power some power b. And then you have u to the b divided by b factorial, q to the d, and then the product of the pi eta I. And then you define a age not to be just the same, except that here you have g m d eta You just have the knot here. U to the power b divided by b factorial, q to the d, product of pi to I. And then 1 plus h bullet is equal to exponent of h naught.
How many ones are there?
As many as you need. You'll have in total a partition of D. And B is also determined. So you don't need to sum over it.
Won't the first object there already start with 1? I mean, if d were 0, so why do you need to put the 1 extra explicitly?
Because it's exponential.
Yes, but won't it already have 1
No.
Implicitly?
No, because 1 should correspond to q to the power 0, which is degree 0. It's not defined as a Hurwitz number.
Excuse me, say-
1 is has no variable. So in particular multiplies q to the power 0. But 0 is d, which is the degree. So Hurwitz number is not defined. So I need to add it.
Okay, thank you.
Okay, and you may think this relation it doesn't give anything nice. But in fact, it's not so true. You can play a lot of games with this relation. So often, people care about connected. Connected are usually more interesting.
Excuse me, I have a question.
Yeah.
What are the Pij? What is it?
Oh, they are all formal variables.
Okay.
There are many formal variables.
Okay.
So let me go through them. U takes care of how many of these simple ramifications you have. Q is the variable for the degree. P, I, eta I take care of these ramifications over here. So you just add a lot of formal variables. You don't care. Every time you have an ingredient, you put a formal variable to remember that ingredient. And so, yeah. Usually the numerative problem is about the connected ones, but they are also the hardest ones. And whereas the disconnected ones are sometimes a little bit easier to deal with. And we saw that already in the Hurwitz numbers with group algebra. When you deal with the disconnected ones, then you don't have to worry so much. Things are, like computations are easier. So for example, if you have, say that you have a recursion for connected, that you want to solve. Then you can transfer this as a differential operator acting on h0 equal to 0 for some differential operator. Aha, but now you can use the fact that you can use this relation and get some d prime such that this is true. And then you get a recursion for the possibly disconnected. But you can also go the other way around. So you can use this kind of reasoning both ways. And usually what you want is a recursion for the connected one. So you want to get here, but this one it's easier to get. So you start from here, then you get a differential operator annihilating that. Then you write this as a d prime applied to exponent of h0 minus 1 equal to 0, right? And now you get this. And from here you get this, and now you're happy.
I mean, for me, it's not so obvious that, you see, in a sense, I can see that relation between connected and disconnected as kind of truncated exponential, okay?
Yes.
So I take the exponential, I take its series expansion, I truncate. So for this reason, I can imagine that going from something I know for H connected to something for H disconnected is simple because I just take the dominant term. But if I go the other way, it's not so easy, eh?
You have to take the log. So it's running.
Take the log, take the log.
Huh?
Take the log is not easy.
Yeah, I agree. I agree. And I'm not claiming that it's easy. I'm claiming that this is a trick people use. And in some cases, it gives a proof of what you...
So just continuation of this question. When you say take the log, this will mean that also you'll have to deal with some non-commutative versions of power series because your operator could have x's and d's that do not commute, or...
you can make it non-commutative, but
right.
so far the variables are... I mean, the differential operator now, yes, of course, you have like derivatives in the p's and multiplication in the p's and so on. Yeah, you need to be a little bit careful and use Leibniz rule.
Right. Like if the operator d was just, let's say, derivatives, then you can exponentiate it and you're fine. But
yeah.
If not, then you'll need to be like quite careful about.
You need to be careful, but sometimes it's not so easy to transfer this differential equation from one to the other.
Okay.
Or maybe I should write an explicit differential operator that annihilates this. Maybe this will make things more concrete. Okay. Maybe I should make an example. Let me skip some stuff. There is one exercise on how to, like if you want to extract a given coefficient. I don't remember which one it is. Yes, there is an exercise that is something like take the coefficient of q to the power 3, u to the power 4 divided by 4 factorial, and the product of all the p, I, j's to the power 0. So you don't have them, right? Take the coefficient of this out of the two sides, and then you do what Marta was saying, that you expand formally this exponent as 1 plus h0 squared divided by 2 factorial and so on until what you need. In this case will be up to the cubic order because every time you have to use at least one q, so you have at most 3 of them, and then you can forget about all the other ones. And then you get then you select the coefficient from left and right, and you have already an interesting relation between Hurwitz numbers connected and disconnected. So this is something that you can try to do to get familiar with formal power series. Yeah. But then maybe I should address this remark. And let me start with a little fact about SD. So I have a simple question. What if you take a permutation? Just take a permutation in SD. And then write it in disjoint cycles. So these are disjoint cycles. And now take a tau, that is a transposition. So this is just swapping I and J in SD. The question is, what is the cycle type of sigma composed with tau? Actually, sorry, I want tau. Okay, it doesn't matter too much, but let me write it on the left. Yes, exactly. Exactly. So the first observation is, okay, if I is in some C and J is another C, then something will happen. But if I and J are inside the same C, then something different will happen. And this is very elementary, right? We're just coming back to first year algebra and doing symmetry group. But actually, this observation over here, it's the beginning of the, if you want, is the beginning of the derivation of topological recursion for Hurwitz numbers. And so what happens is the following. Case 1. That I will call the cut case, by the way. Cut case. Cut case is I and J. They both belong to the same mu n. What is mu n? I want this permutation to be split in this joint cycle, and I call the cycle type of sigma. You want to call it mu1, mu1. Yeah.
Could we just make an example?
Yes.
Take a permutation, split it in cycles,
Yes.
and do T and J, thank you.
Take sigma equal to 5, 4, 1, 2, 3. And take tau 4, 2. This is a computation in S5. And now you ask yourself what is the cycle type of tau composed with sigma. So Marta, what is the cycle type of sigma? 4, 1, okay. 4, 1. So now this 4 here is my mu1, and this one is my mu2. So this is what I wrote here. The cycle type of sigma is mu1, mu-n. Yeah, thanks. Let me call this n. And here is 1. Okay, so we have two cases, as Luca was suggesting. So either I and J belong to Cn. Okay, let me write Cn is more correct. And then what happened is that tau with sigma is of type mu1, mu n minus 1, and then you have an m prime and an m prime prime with the condition that m prime plus m prime prime is equal to mu n. And this can happen in a certain amount of ways. It happens in mu n divided by 2, depending on the parity of mu n, whatever. It happens in, it has a coefficient, as in it can happen in several different ways. So if they are in the same cycle, then the cycle basically splits. Then the cycle splits. We can make an example of this. We can make an example. Say that okay, so this sigma is, for example, 1, 2, 3, 4 in S4. Its cycle type mu1 is equal to 2 and mu2 is equal to 2. And then I want to take tau equal to, say, 1, 2 or 3, 4. Or tau is equal to 3, 4. Right? So I have to take an I and j such that they are in the same cycle. So I only have these two cases. Then what is tau? If I take 1, 2, and I multiply this by 1, 2, 3, 4, I get, of course, this is the inverse of the other. So they cancel out. And then I have just 1, 2, 3, 4. So at the end of the day, the cycle type is what? Cycle type is equal to 2, 1, 1. So I have 2, 1, 1. This is m prime, and this is m prime prime. And if I sum them up, I get 2, which is mu2. Okay, and then we have the join case. And join case is the other one. So if I is in Cn minus 1 and j is in Cn, it doesn't matter, right? They just need to be different. Then I want tau composed with sigma is of type mu1, mu n minus 2, mu n minus 1 plus mu n. Now we can make an example of this. So which tau should I take? Now I should take another tau. 2, 3, thanks. I take 2, 3. So I should do this. 2, 3. And now I want to multiply with 1, 2, and 3, 4. I will do this wrong, but you'll correct me. So 2 goes to 3, and 3 goes to 4, so 2 goes to 4. 3 goes to 2, and then 2 goes to 1, so 3 goes to 1, but I don't know where 3 is. I had to start by 4, sorry. So 4 goes to 3, all right. And then 3 goes to 2, 2 goes to 1, so 3 goes to 1, and now I have a one cycle. And this is of type what? This is of type 4. And 4 is actually 2 plus 2, and this is equal to mu n minus 1, and this is mu n. And so there are no contradictions in signs. Well, this is maybe a bold statement, at least in multiplications in the symmetric group. Do we have the microphone?
If if I could suggest a way to draw it, you have two circles, right? And if they intersect, you just open them and reglue. And if
Exactly.
it's like, I think
Exactly. This is exactly what is happening geometrically.
right.
Yeah.
It's like a Sullivan cheese product,
It's like a?
like a just Sullivan product.
I don't know what you're talking about. But I assume it's something interesting. Maybe you can explain it later. But this is, I mean, this is exactly what is happening on the surface. So now we are just multiplying a transposition. But we know that the transposition encodes a simple ramification. So what we are actually doing is take a Hurwitz number, and now we are plugging one more simple ramification into the picture. What we're doing is, geometrically, if we were counting, here we have our ramification mu over P1. And here we had the simple ramification. So just two sheets come together, and then another simple ramification, and another simple ramification. So each of these is some like ij, right? Now we are adding one more. This is what we're doing. We're adding one more simple ramification. And see what happens. So imagine that we computed already Hurwitz numbers up to some point, and now you plug in another simple ramification, and you see what is happening in terms of the Hurwitz numbers that you had before. Yeah, what about the genus? So now let me write the result. So now this is cut and join equation. So I claim that if you take d over du minus 1/2 sum over I and j, starting from 1. And here you have I times j times the p I plus j, double derivative d over dpi d over dpj minus I plus j pi times pj, derivative in d over dpa plus j. Now you do the following. Apply to h bullet, this is 0. So you can, if you stare enough at this equation, you see that this is exactly what we've been doing so far. If you remember u, if you remember age bullet was something like a big sum with a lot of stuff, and then you had u to the power b divided by b factorial. But u is what? To the power b. B was this Riemann-Hurwitz count. B is the number of simple ramifications, right? So what does it mean to, if you take the derivative in u of u to the b divided by b factorial, you get u to the b minus 1 times b, and here you have b minus 1 factorial times b, and then you cancel out the b's. I'm saying something trivial. I'm saying that this u to the b divided by b factorial is nice with respect to the derivative in u, because when you differentiate, see, they were matching before, and now they match also after. And what does it mean to differentiate with respect to u? Okay, so if you have a power series, a n x to the power n, and you look for x to the power 5, then this is a5, right? But instead, if now you look for x to the power 5 in this guy, the x, say divided by n factorial, now this answer is not a to the 5 anymore. Now the answer is a to the 6. Haha. So you added a simple verification. That was my point, that because we differentiate, we think that we're removing something, but no, we're adding it. Okay, okay. But before it was a5 divided by a5 factorial, so yeah, thanks. Good. So this piece over here, this is insert one simple verification. And this piece over here is, you may join 2 cycles, and this piece you may cut 2 cycles. That's the opposite. Of course, I was going to get it wrong. It's the opposite. The P? Yes, you're right, because actually I simplified a little bit this guy. I want only, thank you, eta 1. Just take one ramification. We're doing simple Hurwitz numbers, so you don't need the index anymore. Thanks. Okay, so this is a cut and join equation. Yeah. And now one of the exercises could be, what is, if this was d prime, what is d applied to h0 going to 0 and equal to 0? I mean, this is for the disconnected, and now you want to transfer it to the connected ones. So, okay, you write that this is equal to exponent of h this minus 1. And then we know how to differentiate exponent. We do the computation, we get some d. And then differential operator applied to power series equal to 0. It's a relation between the numbers. So you get something interesting at the level of the numbers. So I'm out of time. I should go to topological recursion. So if you want, I can point you at some paper where everything is written clearly. It's in the Google Drive folder. That's the paper of Bertrand together with Moulasse and Safnouk. You can find the cut and join equation written as a relation between the numbers explicitly. Okay. So we are here for topological recursion. So of course, I should write the formula on the board. Otherwise, we're not really tensoring with topological recursion. So,
can I now? Okay, lovely. So, you know, this is a theorem, and I guess it's going to be a nice proof. But so far, in a sense, I have the impression that you have to be either very lucky or very clever to come up with a spectral curve. So in a sense, you start doing some computation on certain and crank up with the topological recursion, and then you, oh, look, the Hurwitz numbers or whatever. So, but can I not see this data in some sense from your problem? The data of the spectral curve from the problem. So, for example, now you take the Riemann surface is C star minus R minus. This, for me, this is exactly the Riemann surface you have at the bottom, right?
Yeah.
So, can I use that as kind of an understanding of how to, given a certain problem, how to cook the spectral curve?
Okay, so if you're asking whether it's possible to miss on the initial data, to not see it from a enumerative problem, is that the first part of the question? Suppose you have your favorite enumerative geometric problem.
Excuse me?
Suppose you have your favorite problem.
Yes.
You want to count. And then is it possible to don't have any idea about what the spectral curve is? Is that
yes.
That's the first part of the question? Yes. Yes, it's definitely the case. So how do you guess the spectral curve?
Right.
Okay. So different people know different methods. I know 3 plus going to Santiago walking. That might work. So the 3 methods that I know of are the following. First, look at your genus 0 one boundary problem. That should be y dx. That's something many people do. I mean, many times, I think this is the most frequent method in some sense. Maybe Bertrand will not agree. But he's not here, so fantastic. Second method. You happen to have a differential operator in x and what? D over dx, and usually here you have an h bar, and then you have a wave function that depends on x and h bar, and this is 0. Aha, wonderful. You happen to have this one. So you have the wave function of your problem, and you have some differential operator annihilating it, so you're able now to take the semi-classical limit, whatever it is. So usually you send h bar to 0. And then you get, if you're lucky, you get an algebraic curve. And so now you just guess. This is it. The spectral curve.
Which one? Sigma, sigma, theta?
Again, you're saying something too advanced. You're saying something too advanced. I'm just taking x and y. Just saying x and y, and then I am taking omega 0, 1 of z to be y dx of z, and then I'm taking omega 0, 2 to be this b. And then I'm using topological recursion to compute the other ones. So this algebraic curve, you get it as a polynomial. You get it in the form, if you're lucky, e of x and y equal to 0. And now you parameterize it. If it's genus 0, you find the global parameterization and so on. And then this is a relation between x and y. And you just guess that this is your spectral curve. And then you start computing. Start computing with topological recursion, you get numbers. You take your numbers, you check whether they are correct.
Are there examples in which, are there pathological examples in which you have lovely differential, quantum differential operator? You take the limit, you get a spectral curve, and whoo-hoo, it's not the right one.
See, I lived a good life, it never happened to me. But I mean, in all the enumerative problems I'm aware of, this is always good. Like when you dequantize the quantum curve, you always find a spectral curve. People have been struggling to do the opposite. If you start from a spectral curve, does a quantum curve exist? But once you have the quantum curve, you should be fine, except maybe pathologies that I'm missing on. No, there are no pathologies. Yes, the topological recursion is good. Okay, and the third method. Third method is
Where is this different fluid equation coming from? Like if you have a numerator problem, how would you write down a wave function?
so there is a complicated answer, but the short answer is you have a wave function. You have a wave function. There is some function of x and h bar, and then you just try to annihilate it. That's it.
Where does the wave function come from?
You happen to have a wave function for your problem.
Different methods, different problems. First method, enumerative geometry. Second method, you have a wave function.
Oh, this isn't.
Oh no, it's
trying
not.
to solve
Sorry,
an
it's
enumerative
not
problem.
step by step. It's either you try to attack it with this approach, or you try to attack it with this approach, or you try to attack it with the approach that I'm going to right now. But for example, if you have the partition function for your problem for some reason, well, then you're happy already because you have all the numbers. But suppose you have, okay, maybe you still want to see if it's computed by topological recursion or not. So you take your partition function, you specialize it to the wave function, take this principal specialization. Depends in which setting you're in. There are different ways to do it, but say that you manage to extract the wave function, and now you're just in a D-module problem. You just look for a differential operator, say that you're lucky, and you find it, and now you dequantize it.
Can I make a small comment to illustrate? Well, the first method, for example, for Mirzarani, for hyperbolic volumes, you don't have 0, 1. So you cannot look at the geometric problem for 0, 1, it just does not exist. So you cannot use the first method for hyperbolic volumes. The second method, typically, it's very useful when you have, you said that Okunkov has derived that you had a KP hierarchy. Well, KP usually gives you such wave functions with such operators. So every time you have KP, you know that you have an integrable system, you have the second method, more or less. And that's, in fact, it's very common. It happens in many cases. And what is your third method?
Suppose that you are doing, like, solving some problem in a more algebraic geometric setting, and then you know that your problems, your numbers are integrals over the moduli space of curves of some collection of classes. I mean, this is more for algebraic geometers. Suppose that you know already that you're counting something that is your numbers. Let me write it here. I cannot use this board, which is very annoying. Oh, thanks. Suppose that now you are doing the problem ng mu. This is your favorite problem. And you know already for some reason that you get these numbers by integrating over the moduli space of curves, some nice class. This class Gn. So you have this statement, and now you want to, you ask yourself whether this is computed or not by topological recursion. And if so, what is a spectral curve? So there is a recipe to turn this class, this collection of classes, you need all of them for all G and all N. There is a recipe to turn this collection into a spectral curve, if the collection is nice. There's also a recipe to do vice versa. If you start from a spectral curve, you produce a collection of classes which are nice, such that your numbers are integrals over the moduli space. So you see there is a lot of algebraic geometry behind this. Okay.
I missed this. What is that prime on edge? There is this line.
Oh, I did the following. Let's take this initial data.
Okay.
This initial data, let's guess that this is the correct spectral curve. How do you come up with this? We will see it. We will see it in a minute. We're going to use one of these three to compute what the guess should be.
Can I add a fourth method, which is trial and errors? And it works.
Thanks. Sorry? Yeah, let's just sacrifice them, and maybe one of them will succeed. So you take a spectral curve, and then you produce omega GNs. That's what you were asking. You take this input, and then you throw it in the computer, and you ask the computer to compute omega GNs for you, okay? For large G and large N. Then you stare at these omega GNs. And the suggestion is to expand them in a particular way. Not in any way, but in a particular way. You expand it like that. You expand them near exponent of x equal to 0. You expand them near exponent of x equal to 0. Why would you do it? Because it works. You find some numbers. These numbers depend on several indices. These indices are g and mu, because I'm summing over mu. These mu are the powers of exponent of x, so I need to have them. And then also, I'm adding this extra b, which doesn't matter because it's determined by Riemann-Hurwitz. If that is, maybe you're right. Maybe I should just remove it at this point. I'm defining these numbers by expansion. These are defined by expansion. Of course, you can complain. You can say, like, why does this expansion exist? Well, it exists. You can expand them this way, and you give some numbers. And moreover, these numbers are in Q. And now the theorem is that these numbers are Hurwitz numbers. Yeah. So I should write that h g mu is equal to h prime g mu. And here you would also have your two, let me write it here, let me write it better, h g mu, and then you have your 2, 1, 1, 1, 1, 1 to the b. But here I don't need to write b because b is determined by Riemann-Hurwitz, so it's fine, I can add it. There's no sum over it. It's just completely determined. And they are both connected. Well, this is defined by expansion, so it doesn't matter, but this is connected. There are many non-trivial statements. So first non-trivial statement is you can run topological recursion. Second non-trivial statement is you can expand omega GNs this way. Third non-trivial statement, the coefficients of the expansions are Hurwitz numbers. Yes? Yes. Every time you do something with topological recursion, you have to understand how to expand omega GNs. And there is more. We are aware at least of 2 different spectral curves in which the following thing happens. If you expand near a different point, you find a different enumerative problem.
Is there more information in the topological recursion than in the cut and join equation?
This is a philosophical question, or I think so, but not for the numbers. So I wouldn't say that topological recursion gives you more numbers than cut and join. Actually, they give you the same amount of information at the level of the numbers, And actually, cut and join equation, I think it's even faster. Maybe somebody will disprove this statement. But that's not the point of topological recursion, in my understanding, is that here we have the geometry of the spectral curve, and the cut and join is just some recursion. And also, there's this beautiful magic that happens. Whenever you're dealing with a numerative problem, you have this cut and join equation. Or if you're doing graphs, and you're on surfaces, right? And you can pick 100 different problems of graphs on surfaces. And then you cut one edge, and you try to get some bijection. You get this TUT equation. And each of these equations is different. But when you recast them into the topological recursion, they're just the same equation. So this is the universal form of the recursion, and there is some geometry underneath. But at a level of numbers, it's the same amount of numbers.
Excuse me. Is the wave function that we obtain for this thing known to be the wave function for something from physics? So
yes.
And
yes, this conjecture originated from physics.
No, the psi, the wave function
yes,
that you
also.
write down,
also.
starting from the forms.
Yes.
Is it known to be a wave function for a certain physical
yes.
problem?
So there was this big work remodeling the B model, BKMP. These are the acronym of the co-authors. Then out of that, there was a branching of the project by Bouchard and Marigno that we're staring at. So out of, you have Torri-Calabi-Yau threefolds, and in particular you focus on C3 now. And then the mirror of that is this topological vertex. And then they conjecture that Hurwitz numbers were popping out of that. So the wave function comes from mirror symmetry.
Okay.
And this is a local model. In general, you would attach a lot of these pieces together and make more complicated Torri-Calabi-Yau threefolds.
Actually, let me ask it like this. What is the dx h bar d by dx? Is there an expression for it that you could write down?
It's the Schrödinger equation, if you want.
Yeah, so...
or the Schwanger design.
Yeah, that's what I meant. Where does that come from? Is that for a certain physical problem?
Yes, but depends on the problem. I mean, there are very long answers to this, but I don't think I should dive into them now.
Yeah.
You can run it on the Schrödinger equation with a linear potential. You get your omega GNs, and then you can reconstruct your WKB solution for said Schrödinger equation with the omega GNs. So you can use it to solve the wave equation like that.
Okay. I propose to postpone these questions because they are potentially you can have very, very long answers. You can ask Bertrand, you can ask several people, but I would just postpone them. I'm just multiplying by transposition, and you're asking very philosophical questions. This course is very much down to earth. Okay, but let's. No, I mean it's very interesting. It's just that it deserves more. I think more time. Let's guess the spectral curve. And we just have, let's erase it. Otherwise we cannot guess it. Huh? You didn't write it, right? Okay. So we are going to use, let's use method 1. Let's use method 1. Actually, the way I wrote it is start from a spectral curve and then prove that it's Hurwitz numbers. So I will need to reverse the whole computation, but it doesn't look so good. So allow me to, so I'm going to mess up if I'm trying to, on the spot, reverse the whole computation. Let me do it the way I wrote it, and then you will read it backwards. So omega gn, omega 01 of x of z is y of z dx of z. So if you remember, y was equal to z, and x is equal to minus z plus log z. Okay, so what is this? This is z. Then I have to multiply. This is minus 1, and then 1 plus 1 over z. Okay, but then I multiply here, do like that, and this is the x, and then I can erase this and that. So at the end of the day, I just have 1 minus z dz. So if I take the integral of omega 01, this is going to give me just that. So I'm claiming something super weird at this level. I'm claiming that this, if we are correct,
it's x minus x squared.
Sorry. This must be the generating series for Hurwitz numbers of genus 0 and n equal to 1, which means that the length of your partition mu is equal to 1, which means that we're doing this. This is your partition D, and here you have genus 0 and some simple ramifications. D to 1 over P1. So I'm reversing engineering the guess. I'm saying, like, if this spectral curve is correct, then I just look at omega 01. I know that omega 01 should be y dx. Now I expand it in z. I integrate, and I should get the free energy. This free energy should be z minus z squared over 2. And now, if we're correct, this should be the generating series of Hurwitz numbers with a total ramification over 0. I mean, how would this be the generating series for all these numbers? Like infinitely many numbers.